To be or not to be? Is it spontaneous or not spontaneous? That's the question in free energy and spontaneity. So let's get started here. Okay. When we're talking about, again, the universe, you have to understand that the universe is both the surroundings and the system. We just said that the second law of thermodynamics was delta S of the universe is always positive. But that delta S of the universe is equal to the delta S of the system plus the delta S of the surrounding. Okay. The difficulty there is that you have to be looking at both the system and the surrounding. It's very difficult to do that. Okay, it's very difficult in science to look at both the system and the surrounding. It's much easier to just pay attention to the system. So we're going to try and arrange this equation so that everything is in terms of the system. Okay. I want to remind you about what we talked about last time, spontaneity. When things are spontaneous, there are two factors that are involved. The first is energetics. When things go downhill, exothermic process, that's a spontaneous process because things always want to go to a lower energy state. Spontaneous, but not all endothermic process are non-spontaneous. Some endothermic processes are spontaneous. Who's paying the price to make that process spontaneous? It's entropy. It's entropy. Okay. If the degree of order as you gain energy, as your product become more energetic than your reactant, as long as the chaos or the degree of randomness increases, then that could be a spontaneous process. We talked about that last time. So here, what we're trying to do in this particular discussion is try and describe the universe in terms of the system and use both the enthalpy and the entropy to do that. And in order to get the correct equation for that, we're going to look at how heat is exchanged. When the system releases heat, okay, so that heat is not doing, remember, enthalpy is equal to the heat plus the work. So we're going to ignore the work in this particular case. But when the system releases the heat, that's an exothermic process. The surroundings, therefore, is going to absorb that heat. There's only a two-way street here. When one giveth, the other one has to take. The other one cannot refuse not to take it. Otherwise, that process don't work. Okay, so we're going to take a look at how delta H of the surrounding is, or delta S. Let me clear that. Okay, because I made a mistake there. How delta S of the surroundings can be related to the system, because we want to define the second law of thermodynamics in terms of the whole system and not the system plus the surroundings. Okay, so when delta H of the system releases its energy, then it increases the entropy of the surrounding. Okay, so there's a relationship between delta H system and delta S surrounding, because when the system releases its energy, the surrounding is going to be more chaotic. There's going to be an increase in temperature because of the increase in energy. So what we have here is this right here. Okay, the kinetic energy increases, molecules are moving faster. There's going to be a higher degree of disorder, again, when the system releases heat, and there's going to be a greater entropy increase for the surroundings. So we can say that the heat that is released is related to the entropy of the system, and we put a negative sign there because remember, exothermic processes are negative, and that's proportional to the surroundings. That's proportional to the surrounding. The negative, the heat that is released is proportional to the chaos that the surroundings absorb. And what we need to remember is that there's a temperature factor there. There's a temperature factor there. And the temperature is inversely proportional to the thermodynamics parameter. And that particular equation is this right here. That particular equation is this. So the fact that the temperature is inversely proportional means that low temperature change is insignificant, but high temperature change is significant. Okay, it's like $1 or $100 to Bill Gates or Jeff Bezos. It doesn't really make a lot of difference to their wealth, but $100 to you and me, that can change things. Okay, so that's why it's inversely proportional. And we can rearrange this equation and write minus delta H system is equal to T delta S surrounding. Now we have a equation in which, actually, I went overboard here. This right here is actually an equation that we can plug in to this right here. We can take that and plug it in here, and now we have the universe in terms of our system. And that's what we want, because again, we just want to monitor one or the other, but not both, not both. And so this equation is this right here. Okay, this equation right here. And what we can do is multiply the whole equation by T. The T's will cancel here. And we basically get this equation right here. Oops. I've sort of, we will get this equation right here. Okay, we will get this equation right here. So I'm sort of jumping the gun. Let me go back and talk to you guys about this slide, because this slide really is the ultimate equation that addresses spontaneity. It's based on the second law of thermodynamics. Delta S of the universe is always positive for spontaneous process. 0 if it's at equilibrium. Negative means that the reverse process is spontaneous. And now we have an equation right here that monitors the universe in terms of just the system. Okay, in terms of just the system. So what makes delta S universe positive? Well, remember there's a negative here. So when delta H is negative, a negative and a negative means that that term is positive. And so delta S of the universe would be positive, not looking at this. So a negative delta S exothermic process is going to contribute to the spontaneity of that system. Let's take a look at entropy, this right here. If we look at entropy of the system, entropy of the system needs to be positive for the universe to be positive. So spontaneous process, if you think about it, is always going to be one in which the process is downhill. Okay, the product is going to be lower energetically than the starting. And when you have more chaos, those will always be spontaneous. On the other hand, non-spontaneous process is when the delta S of the universe is negative. That would be an uphill process. And when things become more organized, those will have negative delta S of the universe. So just think about that concept when you are thinking about spontaneity. Look at those two, because those two are factors that determines the spontaneity of a system. So like I said, this right here, we can take this equation and rearrange it so that we have this equation. And then a guy by the name of Willard Gibbs, actually, and he was an engineer at Yale, okay, actually decided that, hey, T delta S maybe that is a new state function. That's a new state function that we could use to put into thermodynamics. And so he made that a new state function, and he gave us this terminology called free energy. Okay, so let's take a look at this right here. This is his biography, but what he gave us was delta G, and delta G equals minus T delta S of the universe. Delta G is actually a reflection of the second law of thermodynamics, because delta G and delta S universe is in that same equation. So this is what we have in terms of free energy, and that's the new state function. That's a new state function. So we don't carry around T delta S of the universe. We substitute delta G for that. So the state functions that we have studied so far is enthalpy, entropy, and free energy. H, S, and G. Okay, H, S, and G. And we're looking for a process in which the change in the temperature is 0 and the change in pressure is 0. So we're looking at a static system when we're calculating this. It's not to say that the temperature is 0. It tells you that between the final and the initial, the temperature is constant. That's what delta T0 means. Okay, so that's basically it. And now we can see that when the delta S of the universe is positive, delta G of the delta G value is negative. A negative delta G means a delta S universe positive. That's a spontaneous process. When delta G equals 0, it's the same as delta S universe equals 0. That's at equilibrium. And when delta G is positive, it's the same as delta S of the universe being negative. That's a non-spontaneous process. The reverse of that is spontaneous. Okay, so make sure you remember that. We're going to be concentrating on delta G from this point on. Okay, we're going to be concentrating on delta G from this point on. So you can think of this as a mnemonic device, just like we had Q. Remember Q when we talked about kinetics? We said that Q relative to K equilibrium. Well, if Q was greater than K equilibrium, then the reaction would go in the reverse direction. That's the way that the equilibrium would shift. If Q was greater, when Q was greater than K equilibrium, then the reaction would go in the reverse direction. When Q is less than K equilibrium, then the forward reaction would be the shift towards equilibrium. Well, we can do the same thing with delta G. Okay, in delta G, what we have here is when delta G is equal to 0, we're at equilibrium. When it's positive, the reverse process is the spontaneous event. When it's negative, the forward process is the spontaneous event. So you can use this as a mnemonic device to figure out the spontaneity with respect to free energy. Okay, but like I said, this is the main equation we will be using. And we can basically take, if this is the system, let me clear this up real quick. Okay, we basically have this. So now we have two ways to calculate free energy. We can do the products minus reactant by looking at the free energy values in the thermodynamic table in the back of the book, or we can do this right here. Delta G equals delta H minus T delta S. So let me just spend 5 minutes to show you an example of that, and then we'll stop there. Okay, next time I will show you, okay, after this discussion, I will show you how free energy relates to equilibrium and electrochemistry. But let's take a look at this right here. Okay, remember when we have F, that's the formation. So we can have a formation for free energy. And we have something under standard state conditions right here. And that's what's found in the back of your book. Okay, products minus reactant. So these are the two ways of calculating free energy. Free energy again, which is indicative of delta S of the universe. Remember, free energy is related to delta S of the universe by T delta S universe. So let's take a look at this. What we have here is methanol being burned in the presence of oxygen to produce carbon dioxide and water. And without doing the math, you guys should see that, yeah, we have a gas, 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 and gas. So the phase change is not going to tell us anything about the entropy change. Let's balance the equation. 2, 3, 2, 4. So we go from 5 particles to 6 particles. So we have more particles in our product. Just based on that, I would say that the entropy is increasing. It would be positive for the system. Without doing any math, just looking at what I have, my balance equation. The phase didn't tell me anything. The temperature is constant. I'm looking at the number of moles that is being produced. And then you guys also know that combustion reaction always generates heat. So delta H is negative. Based on the fact that the entropy is increasing and the energetics is releasing heat, I would say that the delta G for this reaction is negative. In other words, it would be spontaneous. Without doing the math, just looking at what I have here. Doing the math, though, we have these values as found in the back of the book. Now, remember, this is kilojoules. This is kilojoules per mole. So what I did was you use these values and you multiply it by the coefficient in the balance equation to get that value, and then just do products minus reactant. So these are the values as found in the appendix. This would be the value for entropy as found in the appendix. And remember again that entropy is going to be in joules per mole Kelvin. We're using 298 because of the super zero. And then this is the free energy as found in the appendix. Let's do the math. I won't do it for you, but I would have asked you to go in a group, but I knew that this would be towards the end of class. I'll do that next time. But let's do the math. Products minus reactant. If we do the products minus reactant, this is the products. Multiply this by 2, multiply this by 4, and subtract from the reactant. Multiply that by 2. Remember that oxygen is 0. Why is it 0? Because, again, we defined it that in its state, natural state at 298, oxygen exists as a gas, so we assigned it as 0 value. If you do the products minus reactant, we get minus 1351.88 kilojoules. It's not kilojoules per mole anymore because we remove the moles by multiplying by these coefficient. Okay, minus 1351.88 kilojoules. Minus tells you it's an exothermic process, which is consistent with what we predicted. Let's do our entropy. Again, products minus our reactant, it's positive 92.32. So our prediction was correct. Entropy is positive, enthalpy is negative. And if we plug that into delta H minus T delta S, okay, we basically take that and multiply it by that. And again, you need to convert this to kilojoules. You need to convert that to kilojoules by dividing by 1,000. That's why it's 0.09232 in this particular slide. And then multiply it by the temperature. That number comes out to minus 1379.39. Negative tells you it's spontaneous. Negative tells you it's spontaneous. Now let's compare that to products minus reactant. They should be pretty close to each other. If you take products minus reactant, this is the products, make sure you multiply by the moles, and these are the reactant, you actually get 1379.28. That's about a tenth, 0.1 kilojoules difference. That's pretty good. That's pretty good. The magnitude, 1379s are pretty spot on. But again, it goes to show you that there's 2 ways of calculating free energy, and the calculations are not that hard. Okay, these calculations are not like equilibrium where you have to take the cube root of something, or kinetics, where you have to like figure out the order. These calculations are just plug and play. And so it's not difficult. The most difficult thing is finding these values and then remembering to balance the equation. I think we left off with you guys doing some calculations on free energy like this. Okay, so what I want to do next is look at the temperature dependency on spontaneity. So what we want to look at is this equation, delta G equals delta H minus T delta S. Remember that that equation came from the second law of thermodynamics that states that the entropy of the universe is always increasing. And what we did was we look at the entropy of the universe in terms of the system and the surroundings. And then we look at the surroundings, the entropy of the surroundings, and we relate that to the enthalpy, delta H, of the system, because they're going to be related. When the surroundings becomes more chaotic because maybe heat is introduced to it, then that means that the system is releasing that heat. So there's a relationship there where we convert the delta S of the surroundings to delta H of the system. Then what we have now is a way to monitor the enthalpy of the universe by just looking at the system. That was the main thing. And so by rearranging that equation, we got T delta S universe, and T delta S universe, negative of that, is defined as free energy delta G. So I know that there's a bunch of math involved there, but it's just making some substitution. So that's where we are here. Delta G equals delta H minus T delta S. And if we are at standard state, then we would simply put super zeros right here, meaning that we are at 1 atmosphere, 298 Kelvin, okay? But the main parameter in terms of spontaneity is delta G, okay? And what you have is the enthalpy and the entropy at play here, okay? The equation is temperature dependent by this part of the equation. So depending on the temperature, you can make this part, change my ink here. You can make this part more dominant, especially if you have high temperature. But if you have low temperature, then this part becomes the dominant factor in terms of telling you the signs of free energy. Remember, the sign of free energy is what's going to dictate spontaneity. Then the magnitude tells you either how much more spontaneous it is or how much less spontaneous it is. So the signs will give you the red or green light. If it's 0, then it's not going anywhere, okay? And then the magnitude tells you how much more efficient it is or how much less efficient it is. So what we want to take a look at is these two factors, the enthalpy and the free energy. So let me go ahead and erase this real quick. If both delta H and delta S is positive, what does that mean physically? It means that the enthalpy is endothermic, delta H positive is endothermic, but the entropy is spontaneous, more chaotic. So you've got two contradictions in terms of the concepts that will dictate spontaneity, okay? It's uphill in terms of the energetic, but it's spontaneous or it's favorable in terms of more chaos. So which term is going to drive free energy? Well, let's say that we have 1,000 for delta H, just for the sake of having a number, okay? Let's say we have 1,000 there. Then at low temperature, what will happen is that at low temperature, this is going to be small, which makes this part of the equation negligible. Okay, and you might ask the question, well, what's low temperature? Low temperature is for us to figure out when we have delta H and delta S. Okay, there's a switching temperature that you can figure out, and that switching temperature is actually the temperature at equilibrium. Keep that in mind, okay, because sometimes there'll be a question as to what is the equilibrium temperature. And you'll see exactly that that's when one variable, delta H and delta S, are equal to each other. So let's take a look at this. So at low temperature, then this is negligible, and delta G is going to be dictated by delta H. And if we have a positive 1000, that basically means that the reaction is not going to occur. The reaction is not going to occur at low temperature. What's an example of that? Let's say that we want the melting of ice at -40. Okay, the melting of ice at -40 is not going to happen. Okay, because the temperature is too low. What you need to do to melt ice is get the temperature high enough. Okay, so that leaves this right here at high temperature. At high temperature, then minus T delta S becomes the more dominant factor. And because delta S is positive, remember we said that delta S was positive here? A negative times a positive makes that negative. So there's going to be a point where the temperature is high enough that T delta S now becomes bigger than delta H. And now the reaction, or that process, delta G, becomes negative. Okay. So again, this is basically what I'm talking about here in terms of temperature dependence. So let's take a look at phase change. And for this, what I would like you guys to do is take this poll. Okay, you guys should have an understanding in terms of when you need to put in energy for that process to work, it's endothermic, and delta H is positive. If the system releases energy, then that's exothermic, and delta H is negative. Okay, in terms of entropy, if it becomes more chaotic, then that's positive entropy. If it becomes more organized, then that's negative entropy. Okay, so in terms of phase change, you know that when you take, remember, we are at standard state. We're not at -50. We're not at minus or 30 torrs, whereas at standard state, it would be 760 torrs. We're at standard state. So under standard state, if you just take a block of ice, you know it's going to melt. Okay. So first of all, what's happening is that energy is going in, and that's an endothermic process. So for the solid to a liquid, it's an endothermic process. Energy needs to go in. From a liquid to a gas, it's also an endothermic process. Now, I didn't ask the question as to the reverse process because I didn't want to give you guys that many questions. But whenever a reaction or a process in the forward direction is endothermic, then the reverse direction has to be exothermic. Please remember that. You can't have both endothermic forward and endothermic reverse, because remember, in hopefully you guys remember this in thermochemistry, that when you reverse a process or a reaction, then the sign changes. Okay, we're not talking about equilibrium. For equilibrium, it's a reciprocal, but in terms of energetics, the sign changes. Whereas in one hand, the system will release energy. In the reverse reaction, it requires that energy. Energy is conserved, law of conservation of energy. So in terms of enthalpy, solid to liquid, positive, liquid to gas, positive, gas to liquid, negative, energy is released, liquid to solid, negative, and then gas to solid is negative, because you're removing the energy from the gas in order to make it less energetic in its solid state. So to go from a solid to from a gas to a solid, that would be an exothermic process as well. In terms of delta S, okay, what we have is from a solid to a liquid, it's going to be more chaos, more microstates available. Liquid to a gas, we talked about this last time, the gas is even going to be more chaotic, okay? So in looking at the results for some of you guys here, it looks like for the first question, 8 of you said positive, 9 of you said negative. You get a 0 in that question, okay? It's all positive when you go from a solid to a liquid. In terms of entropy for that first question, 11 of you said positive, 6 of you said negative, okay? Solid to liquid, it's becoming more disorganized because the liquid's going to be more random. In terms of liquid to gas, better. Delta H is positive, 12 of you. 5 of you said negative. For entropy, 12 of you said positive, good. 5 of you said negative. And then for gas to a solid, 5 of you said positive, 11 of you, 6 of you said positive, 11 of you said negative. The 11 wins, the 6, it's not an endothermic process, it's an exothermic process. And finally, the last question there, from a gas to a solid, 6 of you said it was going to be more chaotic in the solid state. 11 of you said it would be more organized. So please just use don't overanalyze it. I mean, that's the reason why many of you make mistakes in questions, is you tend to overanalyze things. Just think about the process and think about what you know in terms of water changing phases, okay? The next step to this question would be, what would delta G be, okay? And remember, delta G is spontaneity. Will the water convert to a solid and a liquid at room temperature under standard state conditions? If the answer is yes, then delta G is negative. If the answer is no, then delta G is positive. I won't go into that, but I just want you to be aware of those conceptual type of questions, okay? Those conceptual type of questions. So let's go back to this, because this is an important concept to understand. It doesn't only apply to the phase change of water, it also applies to chemical reactions. So this is a good example because it illustrates to you how delta H and delta S is related in terms of spontaneity. So if we take a look at this equation, delta G equals delta H minus D delta S, we know that when there's a phase change occurring, like at 0 degrees, for example, where solid turns to a liquid at 0 degrees, okay? That's the melting point and the freezing point. Then that's an equilibrium process, okay? If you take a look at the heating cooling curve. Well, if it's an equilibrium process, that means delta G equals 0. Delta G equals 0. If delta G equals 0, you can see from this bottom equation, then delta H minus T delta S must equal to 0. And what you can do is you can rearrange this equation so that delta H equals T delta S. And then if you solve for T, what you have here is delta H over delta S equals T. So that right there is the way to calculate the switching temperature, where it goes from, you know, that ice melting, solid to liquid, doesn't happen below 0 degrees. It's at equilibrium at 0 degrees, and then it's spontaneous above 0 degrees. So if you do this calculation and you get the thermodynamic parameters for water, remember the process is water solid, water liquid. You need to get those thermodynamic parameters. So you have to pay attention to the phases. And you put it into this equation, what you should be able to calculate is 298 as the switching temperature. Okay, that's the temperature at which equilibrium lies. That's switching temperature. So we can basically summarize what we just talked about in terms of this equation, delta H minus T delta S. where T is either going to be low or high. Now remember, there are going to be conditions where it's always spontaneous, no matter the temperature. And what are those conditions? When it's downhill and when entropy is increasing. Okay, when it's downhill, that's negative and enthalpy, that's exothermic. When entropy is always increasing, that's positive delta S. So when you have a delta H that's negative and a delta S that's positive, see, this part of the equation, delta H, would be negative, and the fact that delta S is positive and there's a negative sign here, that means that no matter the temperature, delta G will always be negative. It's always spontaneous. Okay, so a negative and a positive at all temperature, it's spontaneous. On the other hand, it's never going to be spontaneous when it's uphill and you get more organization. Uphill means positive delta H, and more organization means negative entropy. So that's what you see right here. Positive delta H and negative entropy. A negative and a negative right here in front of T delta S makes that whole term a positive. A positive and a positive will always give you a positive delta G. Okay, so it's never spontaneous at all temperature. Now, where does temperature play a role? Temperature plays a role when both signs are equal, when both delta H and delta S are negative or both positive, okay? Because then they're going to counteract each other, and temperature will play a role in that. So this is what happens when it's negative. When both is negative, it's downhill, but becomes more organized. Then that means that at low temperature, where T delta S is insignificant, delta H is going to dictate the sign of delta G, and at low temperature, it's going to be a spontaneous process. But as you increase the temperature, this term, T delta S, now becomes significant because you're multiplying delta S by a big number. Remember, delta S is in terms of joules, whereas delta H is kilojoules. That's 1,000 orders. That's 3 orders of magnitude difference. Okay, so you got to get the temperature up there in order for this term to be significant. But at high temperature, when you get it high enough, and again, the question is, how high is high? You can figure that out by using the equation T is equal to delta H divided by delta S. You can figure out that switching temperature. But if you just look at that equation, let me go back because that's an important equation. Okay, that's an important equation. This equation right here, oops, T equals delta H minus delta S. Well, remember, T is in Kelvin. So if delta H and delta S have different signs, it's physically impossible. Because if they have different signs where delta H is positive and delta S is negative, that means you've got a negative temperature. There is no such thing as a negative Kelvin. Okay, that's why over here, it's going to be either spontaneous or non-spontaneous when they have different signs. But if they have the same signs, both negative, then a negative divided by a negative is a positive. Positive divided by a positive is a positive. So those work, and temperature does play a factor in that. So when they're both negative, low temperature, enthalpy dominates. High temperature, T delta S dominates. And process goes from spontaneous to non-spontaneous. When they're both positive, delta H and delta S, what does that mean physically? It means that it's endothermic. It's an uphill process. But there's more chaos because delta S is positive. So at low temperature, delta H is going to dominate, but delta H is positive, which means that the process will not occur. Delta G is going to be positive. At high enough temperature, T delta S now becomes significant, and the negative there makes that term a negative value. Okay, the negative right here times a positive makes this whole term a negative value, and then it can overtake the positive delta H, and then it becomes spontaneous. So this is a handy chart. I know it might be confusing, but think about the two concepts, energetics and chaos. Okay, energetics and chaos. That's basically the two things that you have to weigh in order to determine whether or not the system is going to be spontaneous or not spontaneous or at equilibrium. That's the key. Okay. So let's take a look at this example right here. We have nitrogen tetrafluoride decomposing to nitrogen difluoride. I can tell you that this is an endothermic reaction. Okay, so I put an E right here. If you can't see it, I have it right there. So you know that delta H is positive, endothermic. Delta H is positive. What can you tell me about delta S? You guys should be able to look at this equation and tell me what the signs of delta S is without looking at the number. You go, this is a balanced equation. They're both in the gas state, so the phase change is not going to tell you anything. But you go from 1 mole to 2 moles. The 2 moles are going to have more microstates. So the entropy is increasing. So both delta H and delta S is positive. It's endothermic and entropy is increasing. Okay, so when you do the calculation, hopefully you can spot check yourself. And when you calculate delta H and delta S, you'll see that they're both positive. And indeed, what I've done was I've done that for you. The delta H for this reaction is 85. The delta S for this particular reaction is 198 joules per Kelvin. Remember that delta H is kilojoules, delta S is joules per Kelvin. So you need a temperature factor in there. So what does this mean? It means that at low temperature, where this term is negligible, it's not spontaneous, because 85 is going to be the dominant term, and 85 is positive. That means this reaction is not going to be significant, or it's not going to be spontaneous at low temperature. At high temperature, this term becomes dominant, and now the reaction becomes spontaneous. So you need high temperature for this reaction to occur. And indeed, this is basically it. Low temperature, delta H dominates, delta G is positive, non-spontaneous. At high temperature, T delta S dominates, it becomes spontaneous. Now the question is, what is the switching temperature? Because you go from non-spontaneous to spontaneous. Well, the switching temperature is simply 85 divided by 0.198. And if you do that in your calculator, remember it's 0.198. It's not divided by 198. And a lot of you will make that mistake because you don't recognize the units. You got to convert both to either joules or kilojoules. So if you take 85 and you divide it by 0.198, what you get is 429.3 kelvins. It's going to be in Kelvin. That's the switching temperature, 423. Temperature lower than that, it's not going to be spontaneous. Temperature at that, it's at equilibrium. Temperature above that, it's going to be spontaneous. And take a look at your lab on thermodynamics, because you've got a bunch of questions like that. Okay, and you can see the same thing here. This is the Haber reaction. Nitrogen plus hydrogen goes to ammonia, and that's an exothermic process. Energy is released. So exothermic process, delta H is negative, okay, because energy is released. And let's take a look at the entropy. We go from gas to gas, so the phase change doesn't tell us anything, but we go from 4 moles to 2 moles. So we're going from more particles to less particles. Okay, just based on that, you know that the entropy is going to be negative. It's going to be more organized, just based on that. So again, we have a scenario where delta H is positive, delta S is negative. So at low temperature, delta H dominates, okay? And delta H is going to drive this reaction in the forward direction. Here are the values for delta H. We said it was negative, and we said that delta S was also negative. It becomes more organized. Exothermic and more organized. is what these signs tell you. So at low temperature, delta H dominates. It's going to be the negative will make delta G negative. So that's going to be a spontaneous process. That's going to be a spontaneous process. Okay. High temperature, T delta S dominates. And the fact that it's delta S is negative, a negative and a negative makes that a positive. So it's going to be non-spontaneous. Then you can also figure out the switching temperature for this. Again, you take 92 and divide by 0.1985 for this reaction to occur. And you can get that switching temperature as shown right there. Okay, so that's an important concept to understand. Why? Because it allows you to predict whether the process without numbers actually is going to be temperature dependent, or it allows you to predict whether it's going to be spontaneous no matter the temperature or non-spontaneous no matter the temperature. Remember, when the signs are the same, it's going to be spontaneous or non-spontaneous without temperature dependency. When the signs are the same, then it's going to be temperature dependent. When the signs are opposite, it's temperature independent. Okay, it's temperature independent. It'll either be spontaneous all the way or non-spontaneous all the way, no matter the temperature. What you need to do is you need to find signs that are opposite each other, and then that'll be a temperature dependent process. Okay, so let's take a look at, we're going to shift gears here and look at free energy more. Free energy and work. Remember, the question really comes to mind as to what's so free about energy. I mean, you always pay for it, okay? The reason why they call it free energy is because that's the energy that's available after paying taxes, okay? When you use energy, you actually have to pay tax, and tax is in the form of heat. And after you pay that tax, the heat tax, then that's the energy that can do useful work for you. So we study thermodynamics, and you guys will see that you study thermodynamics because if you're looking at economics, it plays a big role in economics. It tells you how much energy you need to put in to get that system going, or if you're just putting in money to a money sink, okay? No matter what, it's not going to work. So delta H tells you information about the efficiency of that reaction in terms of spontaneity. The greater the more negative the delta G, the more likely that reaction is going to happen. It's going to give you more free energy in the long run. The more negative it is, you might have to pay you might need to change the temperature, or there might be an instance where no matter what you do, it'll never happen. So that's the reason why we look at thermodynamics. And then we don't really want to waste time if we know that the thermodynamic laws tell us this thing will never work, okay? So what you need to understand, though, that if there is a way to get that process to work, maybe the delta H is small, negatively small, and so it's not very, it'll happen, but it's not a very efficient spontaneous reaction, okay? Or maybe it'll happen and it's very efficient in terms of spontaneous. But remember, spontaneous and rates are not the same. The rate law tells you how fast you reach equilibrium. Spontaneity tells you whether you're going to go in the forward direction or not. They're not the same, okay? They're governed by different rules. And so maybe you have an inefficient reaction at higher temperature, but you try and drive that reaction at higher temperature, even though it becomes the delta G becomes lower, or it comes to a point where it's going to be more inefficient at high temperatures. Why would you drive it at higher temperature? Because you can speed up the reaction. You can get more product at the end okay, at a shorter period of time. So that's the reason why you have to look at the whole story in terms of a chemical process. If you're trying to manufacture, for example, a pharmaceutical product, and you know that high temperature is going to cause less percent yield, but yet it gets you a quicker turnaround time, then you drive it at higher temperature. That's what they actually do in the Haber reaction. In the Haber reaction at high temperature, the reaction becomes less efficient. Yet we drive it at high temperature because we want the kinetics to be fast. We can get more products in a shorter period of time. That's actually a question in your activity for in lab. So think about that. So it makes sense to look at both sides of the coin, the thermodynamics and the kinetics in terms of that. Okay. When you look at delta G, that's actually the free energy. Like I said, that's the energy that can provide useful work. And so we call it W max. W max. And W max is free energy, and it's equal to delta H minus T delta S. I've been harping on that equation for the longest time. Now, if you look at this equation in detail, okay, delta G equals delta H minus T delta S. Delta H is the internal energy outside of pressure volume work. Remember that energy is equal to heat plus the work that particular system will do. If delta P and delta V is 0, that is, there's no PV work, then delta H is just the heat associated with that particular system. Well, the internal heat for say a chemical like gasoline, there's going to be a certain amount of energy in that gasoline through its chemical bonds. But in order for you to get useful work from that, say, gallon of gasoline, you're going to have to convert that chemical energy to mechanical energy. Okay, and then you can drive your car with that gasoline. But in the process of converting that energy through the chemical bonds to mechanical energy, turning your wheels, you're going to have to go through the combustion process. And in the combustion process, guess what? You lose energy in terms of heat. So that's where T delta S comes in. Okay, T delta S. Delta H is the energy from the gasoline. T delta S is the tax you pay in order to convert that internal energy, that chemical bonds, to mechanical energy. That's basically what this equation gives you, okay? The free energy available is going to be equal to the energy available for that chemical minus the energy you have to pay to make that conversion. That's basically what this equation is telling you, okay? So like I said, in the combustion of gasoline, it's not 100% efficient. I mean, if we can get 100% efficiency, that would be great. But only 30% of the chemical energy from gasoline is converted to useful work. Where does the other 70% go? It goes as heat. Frictions on the tire, heat from your exhaust, heat in the engine. No wonder we're trying to get better ways of, we're trying to find alternative fuel, electricity, or hydrogen-powered vehicles, because gasoline is really a bad way of using the natural resources that we have there. Remember that gasoline comes from fossil fuel, and fossil fuel, for the most part, can be used to make different items, organic items. It can make plastic and all that. Most of our fossil fuel, of course, we burn in the form of fuel, but the plastics and even cosmetic lines, the starting material from that comes from fossil fuel. Those are organic compounds that you can modify to make certain things. Anyway, let me move on. Let me also talk to you about why we can never get 100% efficiency. Okay, why we can never get 100% efficiency. Why, when you go to a patent office and they look at your work, they always use the laws of thermodynamics. Okay, so 100% efficiency is never attained. When you take energy and you convert it from one form to the other, you're always going to lose a certain amount of energy. Like I said, that you have to pay the tax, T delta S. So let's take a look at this scenario. You have a battery, car battery. I like to use car analogies because I'm a guy anyway. You have a car battery, it's fully charged. So it has a certain amount of energy that you can use. What do we use that battery for? We use that battery to start our car. So that battery is going to do work on the starter, and the starter will turn and then start your engine. So what happens if we take the battery and we don't charge it, but we keep turning it on so that we always start our car? Eventually that battery will be discharged and it'll reach equilibrium. Batteries never really die, they just reach equilibrium. You learn that in electrochemistry. So it's totally discharged and it's given off a certain amount of work, W1. Okay, now let's say we want to charge that battery to get it back to its original state. How do we do that? We use an alternator. Okay, the alternator allows you to recharge the battery, and that alternator is going to do work on the battery. So that's W2. Okay, so we go from a battery that's fully charged to discharge to back to charge. Okay, so in terms of the battery, it looks like the battery has not gained or lost energy, but the work in order to make that happen is indeed different. Let's take a look at this. If you take a look at work one, that's the work that the battery does to the starter, is equal to the work that the starter receives plus the heat that is generated when you run electrons through the wire. When you run electrons through the wire, there's always heat that's generated. Okay, there's always heat that's generated. If you don't want to lose any heat by running electrons through a wire, you do it infinitesimally slow. But if you do it infinitesimally slow, you can never get the electrons from point A to point B. Okay, but that's the only way to get it 100% efficient. So it's not practical. So work one is going to be equal to, that's the work done by the battery is equal to the work that the starter received plus the heat that is lost. Work two is going to be the amount that the battery receives from the alternator. That's the work that's done by the alternator. In order for the alternator to charge up the battery, then it converts, it works and charge up the battery. But in the process of doing that, remember, the battery has to be connected by wire. You also lose heat because of the electron transfer. Well, that means that W1, W2 is always going to be greater than W1, and they're never going to be equal. Because again, in this process of converting energy from one form to the other, you're paying the tax, you're paying heat loss. So again, this is why thermodynamics is used in a criteria to figure out whether self-perpetuating machines are going to receive a patent or not. And no self-perpetuating machines have ever received a patent. Why? Because it violates the laws of thermodynamics. Okay, it violates the law of thermodynamics. So think of the laws of thermodynamics in terms of, these are the sayings. I remember this when I was taking thermodynamics as an undergraduate student. First law of thermodynamics, conservation of energy. Energy is neither created or destroyed. It's only converted from one form to the other. So in this game we play in terms of energy, you can't ever win. You can't create energy. You can only break even. Okay, energy is conserved. And then the second law comes in and says the entropy of the universe is always increasing. So you can't even break even because there's always going to be a price to pay. Okay, so I found this slide right here that sort of hits the heart and hits thermodynamic at the heart. you can never win, you can only break even. That's the first law of thermodynamics. You can only break even at absolute zero. Okay, at absolute zero, you have zero entropy. So you don't have to pay the price of entropy, but you can never reach absolute zero. We've never reached absolute zero. So that, that these three statements kind of summarize the first two laws of thermodynamics, actually the third law of thermodynamics as well, nicely. So the physical meaning, like I said, the free energy physical meaning is that delta G equals the energy minus T delta S. The internal energy right here, delta H, like the energy in the bonds, equals the free energy available plus the entropy that has to be paid. That's basically it. Okay, so this slide just kind of shows you that relationship right there. Gasoline internal energy, delta G is the amount of energy that actually turns your wheel, but T delta S is the heat loss. Wide range of energy efficiency. These days, whenever we talk about thermodynamics, we always talk about the hybrid cars or electric cars or solar panels and all that. And for the longest time, like in my lifetime, maybe not yours, but we used to have incandescent bulbs. Incandescent bulbs is nothing more than a heat generating mechanism invented by Edison, okay? But it was only 5% efficient. Most of the energy for that incandescent bulb was released due to heat. That's why you could never touch it directly after you turn it on. You turn it on for like even 30 seconds because it generates so much heat. Okay, large electrical generators are actually pretty efficient, 99% efficient. Okay, here are the efficiency of other devices. Dry batteries, 90%. That's why they're so expensive. Car engines, only 18 to 20%. We're now on the verge with these hybrid cars of 37%. Electric cars might be even better. Okay, solar cells, the ones that some of you might have in your roof, they used to say there was going to be a limit of about maybe 20%, but scientists are actually finding materials now that would convert solar energy to electricity at higher efficiency. And this is what the research has shown, that back in the 70s, the most efficient type of solar cell was over here by IBM. It's about 22%, but over the past, it's almost like what, 40 years, okay, we found materials to make solar panels much more efficient. So if you want to go into research, a place where you know there's going to be jobs, you might want to look at energy technologies, whether it be alternative fuels or solar panels. Why do we have an energy crisis? Well, usually we have an energy crisis because we are using fossil fuel when we didn't have alternative energy like solar and wind power. Then we were just basically relying on fossil fuel and coal. Okay, those were the two most abundant, and there's only going to be a certain amount of dinosaurs that died in the past. So we're going to kind of consume that. And then in the process of converting fossil fuel to energy to drive our cars or heat our homes, we're going to release, remember, fossil fuels, hydrocarbon. That combustion is going to generate carbon dioxide. Carbon dioxide is one of the chemicals, and we studied this in kinetics. It's one of the chemicals that can lead to global warming. So we're trying to find alternative ways of generating energy. The sun, of course, is going to be the best way to get energy, because we get almost all the energy in this planet from our sun, except for nuclear energy. Okay, so if we can convert the solar energy to energy that we can use, then hopefully we're not going to be burning fossil fuel. Okay, so that's what you guys need to solve. Your generation is responsible for addressing that. Okay, you guys are going to be the future scientists of tomorrow, and you know there's some legwork that's being done by the current generation and the past generation, but you guys are going to have to lead the way in order to save this planet. Okay, so it's very important you guys do important research on that, because we are a world of energy consumption. In fact, the USA is one of the most hungriest energy consumption nation. We account for 4% of the population, yet we consume about 18% of the energy. Okay, so there's got to be a way to figure out a more efficient alternative for our hunger for energy. Anyway, I just wanted to put that out there. Because it's something that is so relevant in today's society. I'm going to switch gears here, okay? I'm going to talk to you guys about free energy under non-standard state conditions, okay? Under non-standard state conditions. So we've been talking about standard state conditions where we define the temperature and the pressure, but most conditions out there aren't standard state. We don't always have 25 degrees Celsius. We don't always have 1 atmospheric pressure. What happens when we are at non-standard state conditions? Well, when we are at non-standard state conditions, what we need to worry about is a correction term. How can we get the free energy under standard state conditions and correct it so that it will reflect the free energy under non-standard state conditions? Okay, so in order for us to look at this more closely, take a look at this example. Water, liquid water going to basically evaporating, going to a gas. So that doesn't happen under standard state. G is the free energy under non-standard state conditions. G0 is the free energy under standard state conditions. So how do we calculate the free energy under non-standard state conditions? Well, we apply a correction term, and that correction term is RT natural log P. RT is, you guys should be familiar, same RT that we saw in equilibrium. R is 8.314, T is the absolute temperature, and natural log P is the partial pressure of water in this case, since water, gas, vapor, is the only one in the gas phase here. So if we know the partial pressure of water, we can plug it in here and get the free energy under non-standard state conditions. That's the equation we use. For non-standard state conditions, we look at the free energy under standard state conditions and we apply a correction. That correction terms RT natural log P. Okay, so here are the definitions. You can take a look at that. If you want to expand this so that you don't just have one chemical that's a gas, but maybe you have a gas in the product and the gas in the reactant, then that's just products over reactant. You guys should recognize this. That's actually just the reaction quotient. It's the partial pressure of the product divided by the partial pressure of the reactant. Okay, that's what this term is. So this correction term actually brings us back to equilibrium, products over reactant. Okay, but we're not at the equilibrium conditions. We're at the conditions where this is taking place, whatever the partial pressure of the product and the reactant is under at that particular temperature, for example. So this is the equation. This is the equation you would use to calculate the free energy under non-standard state conditions. Delta G reaction equals delta G under standard state conditions. That's what the super zero means, plus the correction term RT natural log Q, where Q is products over reactant. Okay, products over reactant. So let's take a look at this example right here, because I want to demonstrate to you that if you think about what we did in our poll, you have a beaker of water, and that beaker of water sitting there at room temperature, it does not spontaneously boil away, right? Delta G for that beaker of water sitting on your kitchen table is not going to be negative because it just does not spontaneously bubble up and boils away. But if we put the beaker of water on the table, let's say it's a warm summer day, and we come to it maybe like 4 or 5 hours later, we see that the water has evaporated. There's no more water there. Where did it go? It must have evaporated into the atmosphere. Okay, so the fact that it evaporated means that delta G was negative. Okay, the process occurred. Delta G is negative because it was spontaneous. You didn't do anything to it. You just kind of like put it on the table. What's going on there? Logic says that it's not going to spontaneously boil away, but yet if you put it there, it eventually evaporates. Why? That's because when you put it on the kitchen table, you are not at standard state. You are not at standard state, okay? So please remember that the negative and the positive, when you're making that prediction in the poll, that's under standard state conditions. What happens if we're not at standard state? Well, here's how to address that. We have a beaker of water. Let's say we have 1 atmosphere. Okay, so the water vapor is 1 atmosphere, then delta G is going to be positive. It's not going to happen. It's not going to spontaneously evaporate or convert into steam. At 25 degrees, where the partial pressure of water, say we have 100% humidity out there. Okay, you live in Hawaii or somewhere in the southeast where it's really humid, 100% humidity. The partial pressure of water is 0.0313 atmosphere. If you plug that into this equation right here, okay, delta G equals delta G0 plus RT natural log P, you actually calculate a free energy that's 0. It's actually at equilibrium. It's actually at equilibrium. Now, let's say that we go to an environment where the partial pressure of water is really low, somewhere in the desert where it's really dry air, hardly any water. Well, in that particular case, delta G is going to be negative. Delta G is going to be negative. And here's the math, okay? For partial pressure 1 atmosphere, when we plug that in, remember, in the reaction, liquid going to gas. The only chemical that's a gas is the vapor in the product. So it's products over reactant. We don't put anything in the bottom because liquid is not in the mass action expression, only gas or aqueous, okay? So we put 1.0 in for natural log P right here. And when we solve this and put in the values, remember that the delta G for water under standard state conditions, I should put a super 0 right here, okay? It's 8.59 kilojoules per mole. But when we put 1 atmosphere for this term, that term goes to 0 because natural log of 1 is 0. So delta G is just delta G0 positive 8.59 kilojoules per mole. Not going to happen. Not going to happen. It's positive. Suppose we are at 100% humidity where the partial pressure of water is 0.0313 atmosphere. Well, when we put that into the equation, we get this. That term, 298 times R in this case is 8.314. Don't use 0.08206, okay, 8.314. And then multiplied by the natural log of 0.0313, well, that's actually negative 8.59. 8.59 plus a negative 8.59, that's 0. You're at equilibrium. 100% humidity means that the water is just going to stay there. Some of it's going to evaporate, some of it's going to condense. So it's just going to sort of sit there. Nothing's really going to happen because some of it will evaporate, some of it will come in. Let's say that we are in the desert, dry air. So the pressure is 5 times 10 minus 3. Well, when we put that into the equation, we get a negative free energy. So that is what happens when in a summer day when you put your water on the kitchen table and a few hours later it evaporates. That's why this happens, because the partial pressure of water in the atmosphere is much lower than 100% humidity. That's what happens. And so you can use this again to see exactly whether water will evaporate or it's going to condense or you're at equilibrium. Basically is what we just talked about. Here again is just another mnemonic device to show you that there's a relationship between Q and K equilibrium. Remember that when Q was less than K equilibrium, the reaction goes in the forward direction. When Q was greater than K equilibrium, the reaction goes in the reverse direction. That's the same thing with delta G, which brings me to my next topic. There is a relationship between K equilibrium and free energy. There is. When you think about it, when K equilibrium is huge, it means that the reaction is very efficient. K equilibrium being huge, like 10 to the positive 20, 10 to the positive 30, means that delta G must be very negative. Must be very negative. Okay. When K equilibrium is small, 10 to the minus 30, 10 to the minus 20, it means that delta G is probably not going to be negative at all. It's probably positive. Okay. The reverse reaction is going to be spontaneous. So we can see that in this next set of slides. In this next set of slides, we actually look at equilibrium. When equilibrium happens, then Q becomes K equilibrium. We're under the equilibrium conditions. So we're just going to substitute K equilibrium for Q in that equation. Okay, but remember at K equilibrium, this delta G term is zero. This delta G term is zero. Because that's what equilibrium tells you. You're at equilibrium, delta G is zero. So what does this mean? Well, when you substitute K equilibrium for Q right here, you basically get this equation. So you see the relationship between K equilibrium and free energy. There's a negative in front of that so that when this, because you can never have a negative K equilibrium. You can have it very small, but you can never have a negative K equilibrium. But this will change signs when that K equilibrium goes from 1 to -1. Okay, this will change sign. And so that will reflect on delta G. Delta G will either be positive or negative when K equilibrium goes from positive exponent to negative exponent. K equilibrium itself is never negative, but the exponent could be positive or negative. Okay, and so that's what you see right here. These are the two equations that you can use to relate free energy and K equilibrium, or K equilibrium to free energy. That's just the reverse reaction of this if you solve for K equilibrium in this first equation. Okay, so this is found in the back of your lab manual. It's also found at the end of your chapter. Okay, so right here we have acetylene, C2H2. Acetylene is 2 carbons, 2 hydrogens at the end, and a triple bond that connects both carbons. But you can take acetylene and take 3 of them and make benzene, C6H6. If you just take a look at this without doing the numbers, okay, I can't tell you anything about the enthalpy, okay, because I don't know this reaction very well, but I can tell you something about the entropy. You go from 3 to 1, it becomes more ordered. So you know that the entropy is negative, okay? I don't know much about the entropy because I'm not familiar much with this reaction, but if you look up the free energy in the back of the book, benzene's 129.7, acetylene's 209.2. Remember, it's 3, that's the products. It's 129.7 minus 3 times 209.2, because there's 3 acetylenes here. That's minus 947.9 kilojoules. So in terms of this reaction occurring, it's a spontaneous reaction. Minus 497.9 kilojoules. Very negative, very spontaneous. Okay. If we want to look at the equilibrium constant for this reaction, then we just take that 497.9 kilojoules. Remember, that's kilojoules. R is in joules. So you got to make sure, that's a common mistake that you guys will make. You're not getting your units the same. You got to convert either kilojoules to joules or R to kilojoules. So that's what I did here. I took 497.9 negative and I divide by 0.008314 instead of 8.314. I took 8.314 divided by 1,000 times 298. And when I do that, there's a negative in front of that, I get a K equilibrium here of 1.89 times 10 to the 87th. It favors the product. That equilibrium constant is huge. It's huge. Okay. So this right here, I'm just going to go through it, but basically it shows you the relationship between free energy and K equilibrium. When free energy is positive, K equilibrium values are very small. When it hovers between 10 and negative 10, then the equilibrium constant hovers around 1. When the free energy is very negative, then the equilibrium constant is going to be large. Okay, so there is a relationship there. This right here is an exercise that you will find in the announcement in Canvas. This is due Friday. So take a look at it if you want some extra credit points. Okay, this is the question right here. You'll find that in Canvas. It's in the announcement page. It should be released now because I released it at 5:45. So you guys remember that free energy tells you the available energy after you pay the tax, the heat transfer tax of heat, the entropy tax. So what I want to remind you of is that you can calculate the free energy under standard state conditions, but usually you don't have standard state conditions. You have conditions where the concentrations are not 1 molar, temperature is not 298, pressure is not 1 atmosphere, which case you have to apply a correction term. And this is the equation for that. Okay, this is the equation for the correction term right here. But if you're at equilibrium, then Q becomes K equilibrium because you're at K equilibrium, okay? The other thing you should notice is that if you are at equilibrium, delta G equals 0. That's by definition. You're not moving forward, you're not moving reverse, you're at a static point. So when you're at equilibrium, this goes to 0, and delta G 0 equals minus, because you have to bring this to the other side. Okay, you have this equation right here, and you rearrange it so that you have delta G equals minus RT natural log K equilibrium, because now we substitute this in for that. So that's the equation that relates free energy under standard state conditions to K equilibrium in this particular case, because remember, at equilibrium, delta G equals 0. So that's what we have right here. This equation right here is related to delta H minus T delta S. So you can see how K equilibrium is not only related to free energy, but it's also related to enthalpy and entropy. And this is the equation that we are going to be investigating. Okay, so let me go ahead and change the slide here to that point where I didn't cover last time. So this is where we are. Okay, this is where we are. And this is the equation that I just showed you. And so you could set this up so that this is equal to this. And when you do that, you can simplify the equation. Why do we simplify equation? Because remember, scientists like to simplify equation. And if they can put in an equation of a line, then they'll get more information. They can use the data and they can use a series of experiments to show a correlation. That's why we like to put things in terms of an equation. So if you divide by RT, negative RT, so here we're dividing by negative RT, then you have this equation. Natural log K equilibrium is equal to minus delta H over RT plus delta S over R. Well, what is the independent variable? The independent variable is temperature. So if we plot natural log K, that's the equilibrium. Remember that the equilibrium constant is a function of temperature. You change the temperature, you change the equilibrium constant. That's the only thing that'll change the equilibrium constant. So if you plot natural log K versus 1 over temperature, what you should get is a line. Remember, there's a negative slope right here, in which the slope is delta H over R, and the intercept right here is delta S over R. So that's what we're going to do in experiment 7. We're going to monitor the temperature and get the equilibrium constant for a reaction. The reaction is the dissolution of potassium nitrate. That is when potassium nitrate starts to dissolve. It's a pretty easy experiment, except that you have to do that particular experiment about 7 or 8 times. Each trial probably runs about maybe 6-7 minutes. What you're basically doing is just heating up the solution and then cooling it down, then watching when the precipitate starts to occur. At that point, you are at equilibrium. That's when the solution would start dissolving, except you're not really looking at the solution dissolving, you're looking at the reverse when the crystal starts to appear. Because remember, melting and freezing happens at the same temperature. Okay, so that's what we're doing here is when something dissolves, it'll be the same temperature when something precipitates. Rather than watch something dissolve, because that's hard to do, we're going to watch as something precipitates out. Anyway, this is your experiment right here, and this is the relationship that shows the correlation between equilibrium constant, the enthalpy of the reaction, and the entropy of the reaction. So let me go ahead and clear this real quick so you can see that relationship right there. And of course, plot of natural log versus 1 over time yields delta H0. The slope is going to be delta H over R, of course, and entropy. Okay, so that particular part is the whole gist of experiment 7. But what I want you guys to see is the many ways of calculating free energy. The ways of calculating free energy, standard state is products minus reactant. Another way is delta H minus D delta S. Another way is delta G under non-standard state conditions minus RT natural log Q. That's for non-standard state conditions. Remember that equation was originally delta G equals delta G standard state conditions plus RT natural log Q. That was the original equation. We could also relate free energy standard states to equilibrium. And we haven't covered this yet, but we're going to see that free energy is also related to the electrochemical potential. Free energy is pretty amazing, okay? It addresses the question about spontaneity. I enjoy thermodynamics. If you are an engineer, you guys are going to be studying thermodynamics. If you're a biochemist, you guys will be studying thermodynamics because what gives you answers about systems that you are studying. Okay, so that pretty much wraps up chapter 18. What I will do next time is briefly go over those equations that I skipped through right here, because that's related to your lab. Okay, that's related to your lab. So I'll go over that and then we'll hit electrochemistry. But that pretty much takes care of thermodynamics.